The objective of this project was to develop a governing relationship between input and output, as well as design stage uncertainty for the dry thermistor. These were determined utilizing both static and dynamic calibration characteristics. There are two main governing equations used for the dry thermistor: the Steinhardt equation and the voltage divider. The Steinhardt equation gives the resistance of the thermistor at a temperature using values taken from the data sheet for the sensor. The circuit for this experiment was modeled after the voltage divider equation, collecting the voltage drop across the thermistor to calculate the resistance. As the temperature of the thermistor increases, the metal gains more energy. This allows electrons to move more freely, thus decreasing the resistance across it. The experimental setup involved using the thermistor along with a voltage divider circuit. A thermometer was used to measure the reference temperature, and a hairdryer served as the heat source. The static calibration started with placing the heat source 20 inches away from the thermistor with the stream directly on the thermometer and thermistor. The thermistor output voltage was recorded along with the thermometer reading. This was repeated in 2-inch increments, moving the heat source closer to the thermistor until it was 2 inches away. The dynamic portion of the lab involved placing the heat source directly adjacent to the thermistor so it supplied no heat. The heat source was then moved directly in front of the thermistor, and the step response was measured. The three main sources of uncertainty are uncertainty due to thermistor resolution, quantization, thermistor temperature measurement, and the overall design stage uncertainty that was calculated using the individual uncertainties. In this figure, we can see the raw static calibration data, exponential fit based on the raw data, and the ideal curve based on the NTC datasheet. The exponential fit and ideal fit is based on the Steinhardt equation because the Steinhardt equation gives us resistance values, which we can then use the voltage divider equation to get the theoretical voltage output values. One of the standard ways to view the function of the NTC thermistor is by looking at its resistance versus temperature plot, which can be seen in this figure. This plot uses the Steinhardt equation to calculate the equivalent resistance R at temperature T using constants RO, which is defined at a nominal temperature, usually 25 degrees Celsius, and a beta, which is defined for a particular temperature range. Reasons for the discrepancies between the datasheet values and those calculated from the raw data include errors during measurement and analysis, as well as operating at a different nominal temperature and smaller temperature range. If we take the natural log of the Steinhardt equation, we obtain a linearized form which can be analyzed using a linear regression function. The slope of the line represents beta, and the exponent of the y-intercept represents the R0 value. The slope and y-intercept standard deviation values are also obtained using linear regression. The function for temperature can be obtained by rearranging the linearized Steinhardt equation. Using the temperature equation and the standard deviation values, we can calculate the temperature error using the propagation of errors method. Since the data is nonlinear, we need to analyze the overall uncertainty on a point-by-point basis. The experiment temperature range was 44 to 80 degrees Celsius, and the error appears to increase toward 80 degrees Celsius. Slide 12 shows the step response for the dynamic calibration. Based on the z-plot, if we do linear regression on the linear region at around 2 to 4.5 seconds and use the appropriate formulas with the appropriate variables, we get a time constant of 1.3 seconds, which is close to the datasheet value of 1.2 seconds.